80 degrees Fahrenheit. That is the number. Hold it for a moment. Do not move past it. 80 degrees Fahrenheit at 4 in the morning in Las Vegas, Nevada, in March. Not the high for the day. Not the temperature at noon when the sun is at its peak and the asphalt has been absorbing solar radiation for 6 hours. The low. The coldest temperature the city reached over the course of an entire 24-hour period was 80 degrees. A number that, in Las Vegas, belongs to late July. A number that climatologists say should not exist in March in any version of the climate record, not in the modern era, not in the instrumental record going back to the 1870s, not in any reasonable extrapolation of what the climate system was supposed to look like at this point. It existed. It was measured. It was confirmed by multiple stations. And right now, as April gives way to May 2026, the atmospheric system that produced that number is building again. It is larger this time. It is arriving earlier. And the scientists watching it are not using the word extreme the way they used to. They used to use it to mean rare, an outlier, something that falls so far outside the expected range that it cannot easily be placed within the normal distribution of events. That is not how they are using it now. They are using it to mean something they did not have a word for before, a new category of behavior that the system has not yet finished building, arriving at a point in the calendar when every protection designed to manage it has not yet been deployed, inside a framework of understanding that was built for a climate that no longer exists. This video is about the heat wave, but it is not really about the heat wave. It is about what the heat wave reveals. Start with what you have already seen, the headline version, the version that appeared in your news feed and in your weather app and in the forecasts that emergency managers have been issuing in the last 2 weeks. You know the shape of this story. A heat wave is building. Temperatures will reach dangerous levels across the southwestern United States, the southern plains, and parts of the southeast beginning in early May 2026. Cooling centers are being opened. People are being told to check on their neighbors, the usual guidance. That version of the story is real. Every part of it is true. And every part of it is significantly less alarming than what the actual data shows. March 2026 was the warmest March ever recorded for the continental United States. Not the warmest in recent memory, not the warmest in the last several decades. The warmest March in 132 years of systematic temperature measurement, the entire span of the modern instrumental record for the contiguous United States. It ran 9.4 degrees Fahrenheit above the 20th century average. The previous record for March anomaly was roughly half a degree cooler. This March did not inch past that record. It shattered it by a margin that climate scientists described in terms they do not use casually. The event was not confined to one region. 14 states broke their all-time statewide temperature records for March simultaneously. That is not how local weather anomalies work. When one station in one state records an unusual reading, that is a data point. When 14 states break all-time statewide records in the same event, that is evidence of a large-scale atmospheric forcing mechanism operating at continental scale with unusual power. The records did not cluster geographically. They broke across the full breadth of the western and central United States, driven by a single atmospheric structure large enough to impose its signature on 14 separate state climate records at the same time. Martinez Lake, Arizona, recorded 110 degrees Fahrenheit, the highest March temperature ever documented in the continental United States. The previous record was 106 degrees. A 4-degree margin between a record and the new record is not a rounding error. In thermometric terms, a 4-degree departure from the previous all-time extreme for a month across the entire continental United States is extraordinary by any historical standard. Climate historian Christopher Burt, who has spent decades cataloguing temperature extremes from the global record, called the overall magnitude of the March 2026 event, the most anomalous large-scale temperature departure he had encountered in the modern climate record. Yale Climate Connections, which evaluates the significance of extreme weather events globally, classified the March 2026 Southwest United States heatwave as one of the 6 most astonishing weather events of the 21st century. That was March. The system building right now, at the end of April 2026, is operating on top of that record, building in a climate that is already sitting at an elevated baseline from what March left behind. And the meteorologists and atmospheric scientists tracking the upper-level wind patterns say what is coming for May is going to be larger. The surface story is real, but the surface story is not the whole picture, not even close to it. To understand what is physically happening in the atmosphere right now, what is building above the western and central United States, and why it is producing the readings it is producing, you have to start with a specific mechanism. Not a generic explanation of a heat wave which involves sunlight and warm air and summer, the specific physical structure that is creating this event, making it behave the way it is behaving, arriving 6 to 8 weeks before the calendar says it should. It begins in the upper atmosphere, roughly 18 to 30,000 feet above the surface, where the large-scale pattern of high and low pressure governs everything that happens at the ground below. What meteorologists are watching right now is a blocking high-pressure ridge, a dome of dense, descending air that is building and intensifying over the interior western United States. Under normal atmospheric conditions, high-pressure ridges of this character form intensify and then move eastward as the upper-level winds push them along. The western and central United States experiences significant heat for a period of days, and then the system moves on. What is happening now is different in a specific and consequential way. The ridge is not moving, it is amplifying in place. When a high-pressure dome becomes stationary, when the upper-level winds lose the energy to push it along the normal west to east track, meteorologists call it a blocking event. The ridge blocks the normal progression of weather, and the longer it blocks, the more extreme the surface conditions beneath it become. Not because the sun is adding more energy from above, because the structure above is trapping and compressing what is already there. The physical mechanism that makes the surface heat so extreme inside a blocking event is called adiabatic warming. Think of a bicycle pump. When you force air through it into a tire, the pump gets warm. Not because you added heat to it from outside, you did not, because you compressed the air inside it. Compressed air is warmer air. The same process operates in the atmosphere at an enormous scale. Inside the high-pressure dome, air from the upper atmosphere descends toward the surface. As it descends, the atmospheric pressure around it increases, and the air compresses. That compression converts the air's potential energy directly into thermal energy, into heat. The air at the surface under a blocking high-pressure dome is not hot simply because the sun is shining. It is hot because the atmospheric structure above it is continuously forcing warm, compressed air down onto it, day after day, and the surface it reaches is itself heating the ground, and the hot ground is heating the air just above it, and that air has nowhere to go because the dome above traps it. A lid held over a pot does not make the water boil faster because of the heat source. It makes it boil because it prevents the heat from dissipating. The blocking dome is the lid. In Phoenix, Arizona, a metropolitan area of approximately 5 million people, where the urban heat island effect from concrete, asphalt, and low vegetation already adds 6 to 10 degrees Fahrenheit to nighttime temperatures relative to the surrounding desert. The combination of atmospheric compression above and surface heat below is creating a compound heating effect that forecasters are tracking with specific concern. Phoenix has already recorded nighttime lows above 80 degrees Fahrenheit on multiple nights before the event has even reached its peak, before May has properly begun. The Texas grid operator ERCOT issued early season advisory notices in late April, flagging possible high-demand peaks for early May. ERCOT typically issues peak demand advisories beginning in June. The fact that they are issuing them now, before summer has officially arrived on the calendar, is a direct measurement of the magnitude of what the atmospheric models are projecting for the weeks ahead. But the blocking ridge is the mechanism. The pressing question is what is driving it to form at this intensity, at this time of year, 6 to 8 weeks before the climatological window in which events of this character normally appear. The answer to that question requires moving one layer deeper to a structure most people have heard of, but few people understand in terms of what it actually does and how it has been changing. The polar jet stream is a high-altitude river of fast-moving air that circles the northern hemisphere at latitudes between roughly 30 and 60 degrees north. It travels at speeds that can exceed 200 miles per hour. It separates cold Arctic air masses to its north from warmer, tropical and mid-latitude air to its south. And it governs, in fundamental ways, the placement and behavior of nearly every significant weather system in the northern hemisphere. Storms track along it, blocking events develop within its meanders. The heat on one side of its waves and the cold on the other are not accidental. They are the direct consequence of how the jet stream is configured at any given moment. The jet stream is not a fixed object. It meanders. It waves north and south as it circles the globe, and those waves, called Rossby waves, after the Swedish meteorologist Carl Gustaf Rossby, who first mathematically described them in the 1930s, are the primary mechanism by which extreme weather patterns develop and persist in the mid-latitudes. When the jet stream's waves are small and the current is fast, weather systems move quickly eastward, and no single pattern dominates any given region for long. When the waves grow large and the current slows, weather patterns become locked in place. The ridge that produced the heat dome grows taller and more stationary. The trough to its east or west deepens. Both the extreme heat beneath the ridge and whatever weather sits beneath the trough persist for days or weeks rather than days. What atmospheric scientists have been documenting with increasing concern over the past decade is that the waves of the polar jet stream are getting bigger, the meanders are becoming wider, the current is slowing. The technical term for this change is increased meridionality. The jet stream is spending more of its time traveling north and south rather than west to east, which means blocking ridges become taller, deeper, and more persistent. The heat domes beneath those ridges become more extreme, more prolonged, and reach further south than they historically have. The physical reason the jet stream is behaving this way is specific and measurable. The jet stream exists because of a temperature gradient. The pressure difference between cold Arctic air to its north and warmer air to its south drives the fast-moving current. The greater the temperature difference, the faster and more stable the jet stream. As the difference decreases, the jet stream slows and its waves amplify more easily. And the Arctic is warming faster than anywhere else on Earth. Over the past 4 decades, the Arctic has warmed at approximately 3 to 4 times the global average rate, a phenomenon called Arctic amplification. It is driven by a set of feedback mechanisms unique to the polar region. When sea ice melts, it exposes dark ocean water that absorbs solar radiation instead of reflecting it. More solar absorption means more warming. More warming melts more ice. More exposed dark water absorbs still more radiation. The feedback accelerates itself. The result is that the temperature difference between the Arctic and the tropics has been shrinking, and the jet stream that depends on that difference has been responding. Think of it in terms of a table tilted by uneven weight. When one side of the table is significantly heavier than the other, the table tilts sharply and predictably. If you gradually add weight to the lighter side, the tilt decreases and the table becomes less stable, more prone to wobbling in unpredictable directions. The jet stream is the tilt. The rapid warming of the Arctic is the weight being added to the lighter side. What makes the May 2026 situation specifically alarming in terms of this mechanism is the timing. Blocking events driven by jet stream wave amplification have been documented in summer for decades. What has not been well documented until recently is the same character of structure forming with the same intensity in early May, 6 to 8 weeks before the climatological window in which these events are expected. Atmospheric scientists at NOAA's Weather Prediction Center and at the National Center for Atmospheric Research are actively tracking this timing shift as a real-time signal that the seasonal boundaries for extreme heat measurably moving not as a projection, but as a documented observation in the data of the past several years. But the jet stream's behavior is sitting on top of something deeper still. And understanding that layer is what makes the May 2026 heatwave more than a severe weather event. It is what makes it a signal from the entire system. A study published in Geophysical Research Letters in March to 2026 weeks before the heat system now building began to take shape is the most important scientific document for understanding what is happening this spring. Its lead author is Greg Foster. Its conclusions have been described by climate scientists across multiple institutions as the clearest direct evidence yet of a fundamental change in the behavior of the climate system. What Foster and his colleagues did was remove the known natural short-term influences on global temperature from the record El Niño and La Niña cycles, volcanic eruptions, variations in solar output, aerosol forcing from specific documented sources, and examine what remains once those factors are accounted for. The remaining signal represents the underlying warming trend driven by accumulated greenhouse gases. It is the closest available measure of the background warming rate being imposed by human industrial activity. What they found, consistent across all 5 major global temperature datasets independently maintained by NASA, NOAA, Berkeley Earth, the UK Met Office, and the European Union Copernicus program, using different station networks and different calibration methodologies, is that the rate of global warming has approximately doubled since 2015. Not crept upward, not accelerated slightly, doubled. With a statistical certainty of 98%, 5 independent datasets, 5 independent methodologies, 1 conclusion. Robert Rode, chief scientist at the Berkeley Earth Climate Monitoring Group, stated the finding as plainly as it can be stated. The last 3 years are not consistent with the linear trend that has been observed for the 50 years before them. To understand why this matters for the May 2026 heat event, you have to understand what warming acceleration means at the physical level. Warming does not increase temperatures uniformly across the distribution. It disproportionately amplifies the frequency and intensity of events at the extreme end. A 1-degree increase in the global average temperature does not simply raise every temperature measurement by 1 degree. It shifts the entire probability distribution of temperatures, making the readings that were previously at the far edge of the normal distribution occur more frequently and creating temperatures at the very far edge that have no analog in the historical record used to build the models. When the rate of warming doubles, this amplification of extremes accelerates faster than the underlying temperature change would suggest. This is not a projection about what will happen when warming reaches a threshold. This is what the data from the past 3 years shows is already happening. There is a second dimension of this finding that scientists are discussing carefully and publicly, but that has not reached mainstream coverage. The acceleration documented by Foster et al. Is larger than the existing climate models predicted for this period. The standard climate models used by the Intergovernmental Panel on Climate Change projected a warming trajectory that does not match what has actually occurred since 2015. The models are not wrong about the direction. They may be wrong about the speed. One hypothesis for why the acceleration exceeds model predictions involves the 2020 International Maritime Organization sulfur standard, a shipping regulation that required the global fleet to dramatically reduce sulfur emissions from fuel combustion at sea. Sulfur dioxide from ships had been one of the primary sources of aerosol particles in the marine atmosphere, and those aerosols reflect solar radiation back into space, partially masking the warming effect of accumulated greenhouse gases. When the shipping industry converted to low-sulfur fuels in 2020, that masking effect was reduced. Some scientists argue the result is that warming which had been partially suppressed is now expressing itself, and the acceleration since 2020 to 2021 is consistent with this hypothesis. This hypothesis is not established consensus, it is actively debated. The aerosol masking contribution, if real, has not been precisely quantified, and other factors may also contribute to the acceleration. What is not debated, what cannot credibly be disputed, given the 5 dataset, 9, 8%, certainty, finding, is the acceleration itself. The May 2026 heatwave is not sitting on top of a gradually, steadily warming climate. It is sitting on top of a climate that has, as of the evidence available in early 2026, shifted into a higher gear. And yet, for all the coverage of this heat event, the record high forecasts, the cooling center announcements, the emergency management advisories, there is one specific number that is almost never included in the weather apps, the public forecasts, or the emergency warnings. A number that epidemiologists and emergency physicians who study heat mortality say is more predictive of mass casualty events than the afternoon temperature maximum that everyone is watching. That number is the nighttime low. The human body is a heat management system. Every moment you exist, your cells generate metabolic heat as a byproduct of the biological processes that sustain life. At rest, a healthy adult generates approximately 80 watts of thermal energy continuously, the equivalent of a light bulb burning inside the body. During physical activity, that output increases significantly. The job of your thermoregulatory system, the sweat glands, the surface blood vessels that dilate to bring warm blood near the skin, the respiratory cycle is to continuously export that heat to the surrounding environment. That export operates by exploiting a temperature gradient. Your skin surface is warmer than the surrounding air. Heat flows from warm to cool. The greater the difference, the faster the transfer. When the ambient air temperature drops to 65 or 70 degrees Fahrenheit overnight, your body can radiate heat efficiently, reduce the core temperature that rose during the hot day, and recover the physiological reserves that make the next day of heat exposure manageable. When the air temperature does not drop, when a blocking dome traps enough heat near the surface that the nighttime minimum remains above 75 or 80 degrees, that recovery does not happen. The body begins each new day still carrying the heat load from the previous day, having failed to export the accumulated thermal stress. Each day of exposure compounds the physiological damage of the one before. Medical researchers who study heat mortality call this warm night amplification. It is the primary mechanism by which multi-day heat events kill people. Not the afternoon peak temperature that appears on the weather map at 3 in the afternoon, the minimum temperature recorded at 4 in the morning when the body was supposed to be recovering. Think of an engine running without a cooling system. The engine does not fail the moment you start it. It accumulates heat, cycle after cycle, continues operating, continues accumulating thermal load, until the accumulated stress crosses the threshold the system was not designed to handle. The failure arrives not at peak heat input, but when the cumulative, unrelieved load exceeds what the system can absorb. Human thermoregulation fails the same way. In Phoenix, Arizona, during the March 2026 heat event, nighttime low temperatures ran 12 degrees Fahrenheit above their historical average for March, the largest documented nighttime temperature anomaly in Phoenix's climate record for that month. In Las Vegas, 4 consecutive nights failed to drop below 80 degrees Fahrenheit in March. This has no documented precedent for that month in the Las Vegas climate record. At Banner University Medical Center and Phoenix Children's Hospital, emergency physicians documented a 34% increase in heat-related emergency department visits during the 2025 heat season compared to 2022. The majority of those admissions did not arrive in the afternoon. when daytime maximum temperatures peak. They arrived in the morning consistent with the warm night amplification pattern, in which the body's thermoregulatory system does not fail during the hottest hours of the afternoon, but during the night. That was supposed to provide the recovery that would allow survival of the next day. Climate scientists at the National Center for Atmospheric Research have documented that globally, nighttime minimum temperatures are warming approximately 1.3 times faster than daytime maximum temperatures. The metric displayed on your weather application, the afternoon high, is not warming as fast as the metric that determines whether people survive multi-day heat events. The nighttime safety valve is closing. And, for the May 2026 heat event, now building across the western and central United States, the nighttime minimum temperature forecast is not appearing in most of the public-facing coverage. The number that kills people is the number almost no one is showing. What makes the May 2026 situation more than a single severe event? What gives it a systemic character that cannot be captured by any one forecast or any one mechanism is the number of independent atmospheric and environmental systems that are simultaneously active and interacting with it. The heat wave is not happening in isolation. It is happening in the context of three other real and current phenomena, each of which is amplifying the others through documented physical processes. The first is the El Niño developing in the tropical Pacific. El Niño is the warm phase of the El Niño Southern Oscillation, a coupled ocean atmosphere system that produces periodic warming of sea surface temperatures in the central and eastern equatorial Pacific. When El Niño is active, it alters the large-scale circulation of the atmosphere across the entire planet. In the continental United States, its effects vary by region and season, but one of the most consistent signals in the historical record is the suppression or delay of the North American monsoon, the seasonal atmospheric circulation that normally begins breaking the summer heat dome across the desert, southwest of Arizona and New Mexico in early July. The monsoon is the relief mechanism. It is not a guarantee, and it is not always powerful enough to fully end an extreme heat pattern. But it is the primary natural process by which the desert Southwest escapes the summer heat regime in normal years. Without it, the heat persists well beyond what the atmospheric dynamics of a non-monsoon summer would produce. Carbon Brief, drawing on projections from multiple independent modeling centers, reported in April 2026 that the tropical Pacific is developing a strong El Niño event, with model projections showing a median central Pacific warming anomaly of plus 2.2 degrees Celsius by September 2026. That projection, if realized, would place the 2026 El Niño among the strongest in the instrumental record. And it is developing early, approximately 2 months ahead of the 1997 to 1998 event, which remains the strongest El Niño ever documented. The early development is not a technical footnote. It is directly relevant to what is building in May, because the early stages of El Niño are already modifying the large-scale atmospheric circulation patterns that govern where the blocking ridge forms and how long it holds. The monsoon suppression effect, which in a typical El Niño year begins to be felt in June and July, may be operating earlier than any historical analogue suggests. This is not confirmed. The monsoon trajectory under the specific development path of the 2026 El Niño is one of the explicit open questions atmospheric scientists are actively trying to resolve. What is confirmed is the causal connection. The developing El Niño is not coinciding with the May heat event by accident. It is modifying the circulation that produces it. The second system is the drought. As of late April 2026, the United States Drought Monitor shows moderate to severe drought conditions across significant portions of the southwestern United States, the southern plains, and parts of the southeast. Drought is not simply an agricultural problem or a water supply crisis. It is an atmospheric amplifier operating at the surface level in direct contact with the heat dome above. When soil is moist, a substantial fraction of the solar energy striking the ground goes into evaporating water from the soil's surface, from plant transpiration, from the full biological and hydrological exchange between the land and the air above it. Evaporation is an endothermic process. It requires energy, and it draws that energy from its surroundings. The evaporation of water from a moist landscape is the same mechanism that cools your skin when you sweat. The conversion of liquid water to vapor pulls thermal energy out of the surface, but it is leaving. The result is that a significant portion of the solar radiation reaching a well-watered landscape on any given day goes into latent heat, heat stored invisibly in water vapor rather than into directly raising the temperature of the air. Drought removes that cooling. When soil moisture is depleted, there is no water to evaporate, no endothermic conversion to absorb solar energy, no latent heat pathway. All of the solar radiation reaching the surface goes directly into sensible heat, the heat that raises temperatures measurably, that bakes the ground and superheats the air immediately above it. Research by Costa and colleagues at NASA's Goddard Space Flight Center has documented soil moisture feedback contributions of between 3 and 8 degrees Fahrenheit of additional surface temperature warming during heat events in drought-affected regions. The range is not a small signal at either end. 3 degrees is a heat advisory. 8 degrees is a heat emergency. A wet cloth held against skin cools through evaporation. A dry cloth does not. The land surface is the cloth. Drought is the process of removing the moisture that makes cooling possible. The drought across the southwest and the southern plains in late April and early May 2026 is not a background condition with no relationship to the heat event above it. It is actively making the heat event worse, amplifying the surface temperature of the heat dome through the suppression of the primary natural cooling mechanism of the land. The third system is wildfire smoke. Multiple wildfires are burning across the southwestern United States and northern Mexico as of late April 2026. Driven by drought-desiccated fuels and the early season heat, wildfire smoke interacts with the heat wave in a way that is counterintuitive. During the daytime, smoke particles in the atmosphere scatter and absorb incoming solar radiation, reducing the amount of direct sunlight reaching the surface. This tends to depress daytime maximum temperatures modestly. The smoke creates a partial shade that can trim a few degrees from the afternoon peak. But those same smoke particles absorb solar energy during the day and re-radiate it as infrared radiation in all directions, including downward. At night, when the surface is trying to cool by radiating its accumulated heat upward towards space, the smoke layer functions as a partial thermal blanket, absorbing a fraction of that outgoing radiation and directing it back toward the surface. The net effect of a significant smoke layer during a heat dome event is typically a modest reduction in daytime maximum temperatures, combined with an increase in nighttime minimum temperatures, a slightly cooler afternoon, a warmer pre-dawn minimum. That is the worst possible combination given everything already established about warm night amplification and heat mortality. The smoke is not independent of the drought or the heat. The drought desiccated the fuels, the early heat ignited them, and the smoke from those fires is now feeding back into the nighttime minimum problem, the dimension of this event that is already the most dangerous and the least reported. These three systems, the developing El Niño, the drought, the wildfire smoke, are not coincidences sharing a time window. They are a convergent compound system in which each component is amplifying the others through documented physical mechanisms, and in which the compound nature of the whole is producing consequences that none of the components would produce alone. Emergency response capacity is finite. When multiple systems demand response simultaneously, that capacity is divided across all of them. Public attention is a resource that gets depleted. Infrastructure stress is additive. The compound heat event, the heat dome amplified by drought, with its nighttime floor worsened by smoke, with its duration extended by El Niño suppressing the monsoon relief, is not four separate problems. It is one problem that is 4 times harder to manage than any of its components in isolation. The populations at highest immediate risk from the May 2026 heatwave are identifiable. They are not abstractions. In Phoenix, Arizona, a metropolitan area of approximately 5 million people, the urban heat island effect adds 6 to 10 degrees Fahrenheit to nighttime temperatures relative to the surrounding desert. Phoenix is already the hottest major metropolitan area in the United States by average annual temperature, and the urban heat island means that the nighttime minimum inside the city is systematically higher than any regional forecast temperature will suggest. The city's heat emergency management system activates full cooling center operations beginning June 15 under standard protocols. The May heat event arrives before that activation. In a city where the transition to emergency heat management is scheduled to begin in mid-June, an event of this character in early May arrives before the infrastructure designed to manage it is fully deployed. Maricopa County, which encompasses Phoenix and its suburbs, recorded 645 confirmed heat-associated deaths in 2024, among the highest county-level heat mortality totals in the United States. The overwhelming majority of those deaths occurred among older adults living alone without functional air conditioning, and among people experiencing homelessness with no access to cooled interior space. Both populations are present in Phoenix in large numbers. Neither is protected by the standard heat warning systems that assume access to air conditioning exists as a baseline. In California's Central Valley and Texas's Rio Grande Valley, approximately 800,000 agricultural workers are entering the spring growing season as the heat dome builds. California's Division of Occupational Safety and Health expanded its heat illness prevention regulations following the 2021 Pacific Northwest heat dome and subsequent heat deaths among Central Valley agricultural workers. The regulations require shade, water, and heat illness prevention training. Enforcement in remote agricultural areas remains inconsistent. The workers in the fields during the peak of this event are working under rules designed for conditions less extreme than what the current forecasts project. On the power grid, the May timing creates a specific vulnerability that July and August events do not. ERCOT and the Western Electricity Coordinating Council, WEC, which operates the Western United States grid, both typically schedule maintenance operations in spring, taking generation capacity offline for upkeep before the peak summer demand season begins. When an early season heat event produces demand approaching summer peak levels, the grids are operating with reduced available generation capacity and reduced operating reserves at the same time. Demand is rising. The 2021 Pacific Northwest heat dome caused transformer failures and forced load-shedding events across Oregon and Washington. Grid operators have invested in resilience improvements since then. But the early May timing catches both ERCOT and WECC in a vulnerability window that summer events do not encounter. The agricultural system faces a precisely timed threat. Winter wheat across the southern plains, Kansas, Oklahoma, and northern Texas is approaching the grain fill phase in late April and early May. This is the window when the wheat kernel develops its final weight and nutritional content. During grain fill, the wheat plant is acutely sensitive to temperature stress. When temperatures exceed 95 degrees Fahrenheit for even brief periods, hours, not days, during this window, the kernel development process is physiologically disrupted and the yield reduction is irreversible. Cooler temperatures that follow cannot recover what was lost during the heat exposure at the critical phase. Early projections from the USDA Agriculture Weather Facility suggest that if the May heat dome persists through the first 2 weeks of May across the southern plains, winter wheat yields in Kansas, Oklahoma, and Texas could be reduced by 15 to 30% below projection. The downstream effects of a yield reduction at that scale flow through commodity markets to food prices months later, with the largest impact on the households with the least financial buffer. The cascade that follows from the compound event is not hypothetical. Extreme heat drives electricity demand to levels that approach or exceed July peaks. Early May demand peaks arrive while the grids are in their maintenance windows with reduced generation capacity. The probability of rolling outages increases. Rolling outages during extreme heat remove the air conditioning that is the primary protection against heat mortality. The heat mortality surge that follows overwhelms emergency medical systems that are themselves not operating at peak summer staffing in early May. The agricultural yield reduction begins to appear in commodity prices months later, compounding economic pressure on the populations that were already most vulnerable during the heat event itself. None of this requires speculation. It is the direct downstream sequence of documented events and documented vulnerabilities, connected by physical cause and effect relationships that have been observed in previous events and that follow mechanically from what is currently being measured. The scientists watching this event are not simply monitoring it and issuing advisories. They are also trying to understand dimensions of it that current science cannot yet fully resolve. And those specific gaps are worth naming directly, because the dimensions that are least understood are not minor technical details. They include some of the variables that will determine how bad this event becomes. The first open question is attribution. The scientific method of quantifying how much more likely a given extreme event is because of human-caused climate change. Rapid attribution analysis has become standard practice in the years since the 2021 Pacific Northwest heat dome, when the World Weather Attribution Consortium published a finding within 2 weeks of the event's peak. The method works by running climate models under 2 conditions: with observed greenhouse gas concentrations and with pre-industrial concentrations. The probability ratio between the 2 runs quantifies the human contribution. But the methodology was designed for a world in which the baseline, the statistical distribution of temperatures that defines what is normal and what is extreme, was relatively stable. The Foster et al. Finding of doubling warming rate since 2015 raises a direct methodological challenge. If the models being used for attribution are calibrated on historical warming rates that are now demonstrably too slow, then the counterfactual baseline they produce the world without human emissions may also be underestimated. Researchers, including Dr. Friederike Otto, who helped build the rapid attribution field at the World Weather Attribution Consortium, are openly discussing the challenge of applying the methodology to a period in which the acceleration itself was not fully captured by the models. The attribution numbers produced for May 2026 may be underestimates of the human contribution. The scientific community is actively working on how to address this. The second open question is the specific physical mechanism connecting Arctic warming to increased atmospheric blocking. The hypothesis that rapid Arctic amplification reduces the pole to equator temperature gradient, slows the jet stream, amplifies Rossby wave amplitude, and thereby increases the frequency and persistence of blocking events is supported by significant physical reasoning and a growing body of observational evidence. It is also contested in the peer-reviewed literature. Dr. Stefan Vavras and colleagues at the University of Wisconsin have published work arguing for a direct mechanical linkage. Dr. Michael Mann and colleagues have published work arguing that the atmospheric blocking signal is not statistically separable from natural variability in the 150-year observational record. Both research groups are monitoring the May 2026 blocking event in real time as a case study. The event is simultaneously a crisis requiring management and a scientific experiment generating data. The third open question is the behavior of the North American monsoon under the specific development trajectory of the 2026 El Niño. The monsoon is the primary natural mechanism by which the desert Southwest escapes the summer heat dome. Historical composites of El Niño years suggest a suppression or delay of monsoon onset, less rainfall arriving later than in neutral years. But the 2026 El Niño is developing approximately 2 months earlier than the 1997 to 1998 event, the strongest on record. The monsoon response to that unusual development trajectory is genuinely unknown. Some models project a later onset. Some project a significantly weaker monsoon, even if it arrives on time. The range of uncertainty in the projections is wider than scientists would prefer for an atmospheric system on which millions of people in the desert Southwest are depending for relief from what is now building. The fourth open question concerns grid resilience under compound demand. The energy system models used by Lawrence Berkeley National Laboratory, ERCOT, and BUECC were calibrated on historical summer demand patterns, June, July, and August events. They have not been validated against early May heat events that produce demand levels comparable to late July. The probability estimates being generated right now for grid failure under the May 2026 scenario are extrapolations beyond the validated range of those models. The engineers making real-time grid management decisions are operating with tools that were not designed to be applied to the current conditions. There is a fifth dimension of scientific uncertainty that is at the frontier of current research and has not yet reached consensus, but is being actively investigated by atmospheric scientists studying the pattern of the last several years. The standard framework for understanding climate extremes treats warming as a shift in the mean of the temperature distribution. The average goes up, which means the entire bell curve shifts right, which means what was previously rare becomes more common. This framework has been the basis of most risk communication and infrastructure planning for the past 2 decades. What some scientists are now investigating is whether the variance of the distribution, the width of the bell curve, is also changing. If the distribution is not just shifting in mean, but also widening, then events at the far tail are becoming more frequent faster than any model based on mean shift alone would predict. This is not established science. It is frontier, not established consensus. But it is the hypothesis being explored by researchers who are looking at the pattern of the past 3 years and asking whether something more fundamental than a simple upward trend is underway. The scientists watching May 2026 are not in full command of what they are observing. That is not a reassuring observation, it is the opposite. The May 2026 heatwave did not arrive from nowhere. It is the most recent event in a sequence that, when laid out in full, describes something that scientists across the atmospheric and climate community are increasingly willing to state directly. This is not a series of outliers. This is a trend line, and the trend line is steepening. In the summer of 2003, a heat wave settled over Western Europe and remained stationary for weeks. France alone recorded approximately 15,000 deaths. The total European mortality toll reached approximately 70,000 people. It was the deadliest natural disaster in Europe in decades, and it occurred at a global background temperature of approximately 1.1 degrees Celsius above the pre-industrial average. Attribution analyses completed after the event found the occurrence was made at least twice as likely by human-caused climate change. In the summer of 2010, a heat wave settled over Russia with comparable persistence. An estimated 55,000 people died. Crops failed across an enormous swath of the Russian agricultural interior. Wildfires burned for weeks across peat bogs and forests. The background, global temperature at the time, was approximately 1.2 degrees Celsius above pre-industrial levels. On the 29th of June, 2021, a small town in British Columbia called Lytton recorded 49.6 degrees Celsius, 121.3 degrees Fahrenheit. The reading was so extreme that the initial reports were questioned as instrument errors. They were confirmed independently by multiple stations. Lytton burned to the ground in a wildfire the following day. The broader Pacific Northwest heat dome event killed an estimated 1,400 people across the Pacific Northwest and British Columbia within 5 days. Background global temperature, approximately 1.2 degrees Celsius above pre-industrial. In March 2026, the Southwest United States heat event broke 132-year records across 14 states simultaneously, produced the hottest March temperature in the continental United States by a 4-degree margin, and was classified by Yale Climate Connections as one of 6 most astonishing weather events of the 21st century. Background global temperature, approximately 1.5 degrees Celsius above pre-industrial, the threshold that the Paris Agreement identified as the level requiring urgent, aggressive global preventive action. And now, in May 2026, the next event is building. On top of all of that, the pattern in this sequence is not subtle. Each event is occurring at a higher background warming level than the previous one. Each is more extreme than the background temperature increase alone would predict, because warming amplifies the mechanisms that drive extremes faster than it raises the mean. The jet stream becomes less stable. The droughts that amplify surface heat become more frequent. The oceanic heat content that modifies atmospheric circulation increases. The nighttime minimums that should provide recovery become warmer. These drivers compound each other, and the events they produce scale with that compounding, not with the simpler measure of average global temperature. The 9.8% certainty warming acceleration documented by Foster et al. Means this pattern is not continuing at the same rate it followed from 2003 to 2021. It is steepening. Climate scientists who study long-term temperature trajectories draw a distinction that matters here. There is a difference between a trend, a steady movement in a direction, and a phase transition, a point at which a system shifts to a fundamentally different mode of operation. The familiar example is the transition between ice and water. Temperature rises gradually, and then at exactly 32 degrees Fahrenheit, the system changes state in a way that cannot be reversed by returning to 31 degrees. The question that the pattern of the past 3 years is raising, and that the Foster et al. Acceleration evidence is making more urgent, is whether the climate system is undergoing something analogous to a phase transition, not simply trending toward more extreme events on a stable trajectory, but moving into a new operating mode in which what was previously extreme becomes the baseline, at a speed that existing frameworks did not anticipate and cannot yet fully describe. This is not settled science. It is the question the data is generating, and the May 2026 heatwave is the latest piece of evidence being placed in evidence. That brings the question into sharp focus, the forward question, the one the data has produced, and the one that does not have a comfortable answer. If global warming has genuinely entered an accelerated phase established at 9.8% statistical certainty across 5 independent datasets, consistent with the pattern of the past 3 years, and larger than the models predicted, what does it mean for heat risk management when the baseline that defines extreme is moving faster than any infrastructure, medical system, emergency response framework, power grid planning model, agricultural risk projection, or scientific attribution method that was built to protect human life from it? This is not a question about decades from now. It is a question about now. The cooling center protocols that activate in Phoenix on June 15 were not designed for a major heat event in early May. The grid demand models that determine how much reserve generation to maintain were not validated against early May compound events with late July peak characteristics. The attribution methods used to quantify the human contribution to extreme events were not designed for a warming rate that the models themselves did not predict. The heat mortality surveillance systems that tell public health officials how many deaths to anticipate are calibrated on exposure-response relationships from periods when the nighttime minimum was providing the thermoregulatory recovery that the evidence suggests it may no longer be providing consistently. Each of these frameworks was built for a previous version of the climate. The May 2026 heatwave is operating in the current version. That gap between the frameworks that govern how society understands and responds to extreme heat and the actual behavior of the climate system producing the heat is not a future problem to be solved. It is a present condition being lived through by the 5 million people in the Phoenix metropolitan area, by the agricultural workers in the Central Valley, by the grid operators issuing early season advisories they were not expecting to issue for another 6 weeks, by the atmospheric scientists watching a blocking ridge form in early May with the character of a July event. The question does not have a comfortable answer. It may not have a fully worked out answer at all. What it has is urgency. And what the May 2026 heatwave has is the specific quality of a situation that has moved beyond the frameworks designed to contain it, arriving at a point on the calendar when those frameworks had not yet been deployed. 80 degrees Fahrenheit, 4 in the morning, Las Vegas, Nevada, March. You know now what that number means. You know about the blocking ridge and the compressed air descending onto a desert city where the concrete and asphalt of the urban heat island have already added 10 degrees to what the surrounding desert would produce. You know about the jet stream's wider, slower waves, the Rossby waves that are amplifying because the Arctic is warming at 3 to 4 times the global average, shrinking the temperature gradient that gives the jet stream its speed and coherence. You know about the warming acceleration, the doubling of the rate of warming since 2015, established at 98% certainty across 5 independent datasets by 5 independent research teams using 5 different methodologies, all arriving at the same conclusion. You know about the nighttime minimum, the number that predicts heat mortality, the number that is warming 1.3 times faster than the daytime high, the number that was 12 degrees above the March average in Phoenix during the March event, the number that kept Las Vegas above 80 degrees for 4 consecutive March nights, with no precedent in the climate record, and you know that this is the number almost no one is showing you. You know about the El Niño developing in the tropical Pacific, projected at plus 2.2 degrees Celsius in the central Pacific by September, developing 2 months earlier than the strongest event on record, already modifying the circulation that will determine whether the desert Southwest gets monsoon relief and when. You know about the drought amplifying the surface temperature of the heat dome by eliminating the evaporative cooling of the land, 3 to 8 degrees of additional warming from dry soil, documented and measured. You know about the wildfire smoke worsening the nighttime floor while the afternoon television cameras are pointed at heat shimmer rising from highway asphalt. You know about the 645 confirmed heat deaths in Maricopa County in 2024 and the cooling center protocols that activate in June while the event is building in May. You know about the winter wheat in Kansas and Oklahoma at grain fill phase, 95 degrees away from irreversible yield collapse. You know about the grid in its maintenance window while demand is headed toward July levels. You know the pattern. 70,000 in Europe in 2003, 55,000 in Russia in 2010, 1,400 in 5 days in the Pacific Northwest in 2021. One of the 6 most astonishing weather events of the 21st century in the southwest United States in March 2026, 132, year records broken across 14 states before May had even arrived. The number at the beginning of this video was 80 degrees Fahrenheit at 4 in the morning in Las Vegas, Nevada in March 2026. It exists because the jet stream's waves are wider than they were. It exists because the Arctic is warming faster than anywhere else. It exists because the nighttime atmosphere retains more heat than it used to in a way that is measurable and documented and accelerating. It exists because the climate system, as of the evidence available in early 2026, is operating at a rate that the models designed to describe it did not fully anticipate. The number is not going back to where it was. What is now building across the western and central United States in the first days of May 2026 is the current expression of everything that has been accumulating in the atmospheric system for years. The wider jet stream, waves, the warming Arctic, the drought-desiccated land, the developing El Niño, the confirmed acceleration that no existing framework was designed to manage at the speed it is moving. The scientists watching it are not using the word extreme carelessly. They are using it the way you use a word when you have run out of historical context to compare against. What is unfolding now is not an extreme version of something familiar. It is the first version of something the record has not seen before. Arriving in a month, the record was not prepared for it. Inside frameworks that were built for a world the data says no longer exists.